All right, so next up, I would like to introduce our next speaker, Lenny Giuliano, who will be presenting TreeDN, tree-based CDNs for mass audience live streaming. Lenny is a distinguished systems engineer at Juniper Networks and has traveled from Herndon, Virginia to speak with us. This is Lenny's second time presenting at NANOG. Lenny's first talk was at NANOG 62 in Baltimore 2014. Welcome to the stage, Lenny.
Thank you. So today I'm going to talk about a CDN technology that is designed to bring Steph Curry, Mark Andreessen, and Taylor Swift into your living room, possibly all at the same time. So let's start with what is the problem we're trying to solve here. In the last 17 months or so, we've seen audiences for certain live streaming events explode to the point where it's putting real strain on network resources. With increasing bit rates like 4K, 8K, and augmented reality coming down the pike, it's only going to get more difficult, more challenging to support this from a network perspective. So I mentioned 17 months ago, that's when Amazon Prime first started showing Thursday Night Football. And this was the first time that NFL football was being streamed on the internet exclusively. So for 3 hours a night, 16 nights a year, they have 10 to 15 million viewers for the last 2 seasons. Comcast came out and said a quarter of all internet traffic on Thursday nights is this one game. It continued on this year with YouTube TV having exclusive rights to NFL Sunday Ticket. So for the first time, NFL Sunday Ticket was exclusively streamed online. And just last month, the first ever NFL playoff game was streamed exclusively online on Peacock. That had a US record of 23 million viewers. Now the numbers for cricket are just mind-blowing. Started with the IPL finals last June, in June of last year, where they announced, I believe it was a world record at the time, of 32 million concurrent viewers. A few months later in November in the World Cup, they shattered that record and continued to do so in quick succession. It was like the quarterfinals was 43 million, then the semifinals was 53 million, and then the finals was 59 million concurrent streams. Live streaming today is responsible for 17% of all internet traffic. In 2015, it was less than 1%. Now, some people say, video's video, right? What does it matter whether it's somebody's watching a Netflix movie on demand or a football game? Video's video, shouldn't matter whether it's live streaming or not. Well, the fact is live streaming is fundamentally different than on demand for a few reasons, primarily latency. If you're watching a movie, you can live with a playout buffer of a minute or two because it's a movie, who cares? It came out weeks, months, years ago. If we're talking about a sporting event, you run the risk, if you have a playout buffer that long, of getting a text message from your friend telling you about the game-winning score, or hearing everybody cheering at the bar across the street a minute before you see what happens. So to match traditional broadcast television, you have a latency budget of about 5 to 10 seconds. And if you want to do something like micro betting, where you can bet on, will the next pitch be a ball or a strike? Or will they score on this series? Will they get a first down or not? Not the most, admittedly, not the most inspirational use case, but certainly you can imagine very lucrative. And to do that, you're talking about something closer to a latency budget of probably less than a second. The other thing is join rates. Everybody in this room who operates a network is very familiar with that typical diurnal pattern of traffic flow in your network. where it goes up during the day, comes down as people go home, and then skyrockets during the evening as people start streaming. Now that's a huge difference between peak to trough, but it's smooth and predictable. It's roughly the same every day. When it comes to live streaming events, these mass audience live stream events, it's more like a step function. As everybody tunes in just as the game's starting and everybody tunes out just as it's over. Just one other thing to keep in mind. Thursday Night Football is not available in 4K. Just something to keep in the back of your mind. So I mentioned some of these content providers for these big events. They've spent a lot of resources. You know, think about Amazon Prime, you know, with all the resources they have, all the CDNs they use. They and the others who are broadcasting these events, really their goal is to be almost as good as television, or just about as good as television, right? And the thing about the internet is it's supposed to be better. It's not supposed to be just as good or almost as good as what we've had for the last 70 years. It's really supposed to be a medium that brings us experiences we couldn't have gotten otherwise. For example, what if you wanted to know what it's like to sit courtside at a Golden State Warriors game, where to the left of you is Mark Andreessen and to the right of you is Adele. And you could hear Mark talking to Adele, and you can see Steph Curry knocking down threes, talking, see Draymond tripping people. To get that experience would cost you about $10,000. That's how much front row center court tickets generally run for those games. You'd have to pay $40, $50 for parking and another $17 for a beer to get that experience. And you, of course, run the risk that, you know, right before the game, Steph is sitting this one out. After you've purchased all this, Steph is sitting out for load management, right? So what if instead of paying 10 grand for that experience and $17 for that beer, you could just throw on some AR goggles and get that same experience and look, and you could see Mark Andreessen to the left and Adele to the right, and you can hear them talking to one another, hear what they're saying. And you can see what's going on with some of the most exciting basketball players to ever play the sport. And instead of paying 10 grand for that, maybe it costs, I don't know, $200, $300. And you can wait till right before game time to make sure Steph is playing in this one before plunking down that money. Well, here's a question. Can the internet support that? Imagine tens of thousands, hundreds of thousands, perhaps millions of people wanting to get that experience. Could the internet do that? Is that possible today? This concept of mass streaming, mass audience live streaming in AR. Can the internet do this today? Or better yet, what about getting that experience of being a fly on the wall in the Kelsey box? Where just think of how many people and how much they would pay to get that experience, to see what it's like to be in that suite with Taylor Swift, talking to her boyfriend's mom, with the crazy shirtless brother in the background. Think of all the Swifties who would be interested in what they might pay for that experience. And think about this from the perspective of, you know, say the NFL. They come for Tay-Tay, but they discover and stay for Patrick Mahomes and learn, this football thing's pretty cool. And they become potentially lifelong fans. Just imagine how valuable such a thing could be. And again, could the internet support this today? For tens of thousands, hundreds of thousands, maybe millions of people wanting to gain that experience, that incredibly high bandwidth experience. Something to think about. So, the obvious implication here is, in order to scale from a data plane perspective, to deliver this kind of experience in the network, it implies some level of network-based replication. Multicast. So multicast has been around for 3 decades or so, and it has been fairly successful in some places. On financial networks, absolutely vital. It's a critical service. Video distribution, very commonly used. It's kind of table stakes, and MVPNs are, a basic function of any layer 3 VPN service. And some enterprises have been relying and depending upon multicast for decades. But all of these are walled garden networks. What about internet multicast? Live, over the top, live streaming internet multicast. Well, not so much. It's tough not to call it an abysmal failure. But it's worth asking what went wrong, right? And there's really three big problems for internet multicast of why it never really happened. First problem is, and the biggest problem, the all or nothing problem. In order for multicast to work, every single layer 3 hop from source to destination needs to be multicast enabled. Every interface on every router and firewall on the internet essentially needs to be running PIM, a routing protocol like PIM. And it's really hard to do. It's really hard to get every interface on every layer 3 hop on the internet to support some new set of protocols. Just ask the V6 people. They've been dealing with the same problem for just as long and are not doing a whole lot better. Maybe a little bit. The other problem is operators, since the dawn of multicast, have complained about how complex and difficult it is to manage and operate a multicast network. So in places where that perceived benefit is worth the cost, it's been deployed, like financial networks. And in other places where the juice has not seemed to be worth the squeeze, it hasn't. And then there's the chicken and egg problem, where there's no multicast content because there's no multicast audience. There's no multicast audience because there's no multicast content. The good news is multicast has evolved over the last 2 decades to address, and we're at a point now where it can address all of these problems. And essentially that's what TreeDN is. It's a tree-based CDN, and it leverages 2 things, 2 components that I'm going to dive into: a native component and an overlay component. And the key thing is it delivers a service to end users wherever they are, whether they're on a multicast-enabled network or not. And they are not dependent upon their last mile provider. Some of the nice benefits: incremental deployment. You get the parts of the network that are multicast enabled enjoy the benefits of multicast. And the parts that aren't, well, they just get tunneled over. But the key thing is the end user gets the content. They get the service. The end user doesn't care whether it's unicast or multicast. They just care that they get it. Now, the transport provider and the content provider, they might care. Certainly much, much cheaper to distribute. But the key thing is you can deliver a service and expect that service to be received. And that's what TreeDN is. And I'm going to kind of dive into these components. So the first part is the native, we'll call it on-net. This is the part of the network that is natively multicast enabled. The key part of this is SSM, source-specific multicast. So it turns out multicast is not complex. Network-based source discovery is complex. You see, multicast, as it was originally designed, we call it ASM, any source multicast, had the fundamental assumption that the network was responsible for finding sources. An end receiver who was interested in joining a multicast group would just say to the network, I want to join this group. I don't know who the sources is. Network, you figure it out for me. Well, when the network is responsible for source discovery, it has to do things like it needs rendezvous points, and it needs PIM register encap and decapsulation. You have shared tree behavior, you have tree switchover, you have MSDP. And all of these really complex, difficult to implement, data-driven state creation events. Well, SSM eliminates all of that. SSM says the end host is responsible for source discovery. How does it figure it out? Some magical way out of band, say the application layer. Short answer is if it figured out who the group is, it should be able to figure out who the source is. And the end host, the receiver, tells the network, I want to join this group from this source. So it gives it that hint. And by telling the network who the source is, things are vastly simpler. You eliminate about 90+% of the complexity of multicast by using SSM only. Now, I realize, being at an IETF, there are probably people in this crowd who are mentally queuing up and can't wait to get to the mic to talk about how in 1999 they had a 2500 under their desk that they connected to the MBONED and it would, constantly crash on some obscure PIM RPT bug. Or in 2003 they hit an MSDPSA storm and they got a headache reading the pure RPF rules. Or Biter melted down their data center 15 years ago. And you're right. I am not gonna okay boomer you. You're absolutely right. Multicast was way too complex. And we heard you. The people who've been working in the multicast working groups have been working diligently to eliminate all those issues. And all that baggage of the past, all those things you hated about multicast are network-based source discovery related. And those are completely irrelevant to this architecture. And that's what this architecture is. We've addressed and learned the lessons of the past that made this not very optimal. I mean, just think, we asked multicast to do too much. It was the functional equivalent of asking OSPF, we never would have asked OSPF or BGP to keep track of a global database of every single web page on the planet and keep that in routers. And yet that's essentially what we expected with ASM. And predictably, it didn't work. All irrelevant with SSM. The second part is overlay networking. So when I began in this business in the late 90s, tunneling was seen as a suboptimal hack to be avoided and eliminated. But now, if we just call it overlay networking, all the cool kids are doing it. So we're taking advantage and we're riding the wave of fashion and leveraging overlay networking, specifically a technology called AMT, Automatic Multicast Tunneling. What AMT does, I'm going to dive into the details, but essentially at a high level, it builds tunnels dynamically. When we think about tunneling, we think of like maybe GRE, where you have these static router-to-router tunnels. AMT, what's interesting about AMT is they're dynamic, they're ephemeral, and they're between routers and hosts, not routers and routers. And it enables devices that are on unicast-only networks. And when I say host, I'm talking about smartphones, laptops, Fire Sticks, smart TVs. They can tunnel to the parts of the network that are multicast-enabled, receive the content, and they're not dependent, and they hop over the parts of the unicast network. They're not dependent on their last-mile provider to deliver multicast natively. So this solves that all-or-nothing problem where every single hop needed to support PIM. It also solves that chicken and egg problem by allowing essentially every host on the internet to be a potential audience member. All right, so what is AMT? How does it work? What is AMT? Again, is automatic multicast tunneling. Well, let's imagine you have a multicast-enabled service provider. There aren't many of them, but they do exist. And imagine you have a multicast-enabled content owner. Again, there's not many of them, but they do exist. And imagine there's a multicast-enabled local provider. Not a lot of them, but there's a few. So imagine you have a bunch of receivers on that local provider who are interested, and they receive multicast natively the way God intended, where no single link carries more than one copy of the data stream. Now imagine the other 99% of the internet, which is unicast only, and you have an interested receiver who sends an IGMP report to its last hop router. That last hop router isn't multicast enabled, doesn't know what to do with it. However, this end receiver has a thing called an AMT gateway client. And that's basically the tunneling client. And that AMT gateway is able to one, magically discover a thing called an AMT relay. The relay is a tunnel server, and it dynamically builds a UDP tunnel to that receiver. Once that tunnel is up, through that tunnel, it sends an IGMP report. The AMT relay receives that IGMP report, turns it into a PIM join, receives the content natively, and sends it through the tunnel as if this gateway was a directly connected receiver. As more receivers, interested receivers pop up, they each get their own separate tunnels. Now notice here, at this point, that unicast only network suddenly, for the first time ever, has a motivation and an incentive to actually turn on multicast natively. If you get to the point where you are suddenly carrying tons and tons of duplicate unicast streams that could easily be replaced with a single multicast stream, you suddenly have a reason to actually turn on multicast natively. So you can think of AMT as kind of like a transition mechanism, a stopover, not a destination. There's always going to be parts of the last mile that don't support multicast. So AMT will always have its place, but it's a critical transition mechanism that gets stuff working so that we can optimize it later. Another point, for those of you who are wondering, how do you make money off of this thing? Well, just look at, say you're a multicast-enabled service provider, the big thing in the middle, and maybe part of your network is the multicast-enabled local provider. You are also the local provider. So you have a native network plus native receivers, eyeballs directly connected to you. You could go to one of those content providers and say, hey, you're sending tens of millions of streams. You're using, I don't know, 5 different CDNs today, spending an inordinate amount of money on them. Why don't you try us for your 6th one? Send us a native multicast stream instead of, the unicast streams you're sending. And we have native receivers, native eyeballs, and we'll deliver your content to them free just because we like you and we're really nice. But we have these things called AMT relays for receivers who might be off our network, off-net receivers, and we'll charge you for that on a per tunnel basis or per bits through that AMT. So we'll charge you for that AMT traffic. But that's going to be a fraction the cost of what you're spending today on the existing CDN technology. And I'm going to talk about why. So essentially, what is TreeDN? It's just SSM and AMT. Both of which have been around for a long time. There's nothing new here. What's new is we've taken these components, these old components, and kind of synthesized them together in a way to deliver a service, to provide a CDN service, in a way that's to address a problem that is an acute problem today. So you have the big I internet, that's unicast only. You have a TreeDN provider, that is native, that's the on network. You have native sources, native receivers on net. And then if you have a receiver off net, on the unicast only network, we deploy these relays, we send the traffic natively to the relays, and we tunnel it to the receiver. Now, some of you might be saying, wait a minute, how's this different than a CDN? Isn't this what a CDN does? It's an astute observation. And yes, I mean, essentially a CDN is doing network-based replication. CDNs essentially do multicast without doing multicast. They're doing unicast to unicast replication. And there's different models for CDNs, but typically you have these CDN boxes deployed throughout a network. The origin sends content to those boxes, and then they handle local replication. It just works. You don't need every single interface on every router and firewall on the internet running PIM. All right, so let's look at this CDN with multicast, essentially a TreeDN. First thing we're going to notice is those CDN boxes. We're going to rename them. We're going to call them AMT relays. We're going to send traffic from the origin to the relays that have interested receivers nearby, and those relays handle local receivers. So it does kind of the same thing, right? Well, there's a couple fundamental differences. If those AMT relays, if you have routers at the border of your network that are capable of doing AMT inline, and there are different vendors. This is an open standards-based solution supported with several different implementations from several different router vendors. And if you happen to be fortunate enough to have devices at the edge of your network that support AMT, you can essentially turn those routers into CDN boxes. The nice part is you don't need new hardware. You don't need new licenses. You just, for as little as a cost of 5 lines of config, paste it into those routers that are already there. You can add this CDN services. Because in a CDN, in traditional CDNs, those CDN boxes are actually racks and racks of x86 servers. x86 servers that need to be racked, stacked, powered, cooled, and plugged into revenue-generating ports on your routers. Well, you can eliminate all of that by just turning it on your routers if you have devices that can do that. So essentially, it's like a CDN on a chip. You can argue, so it's essentially for zero CapEx, you can offer this service. And because it's not sucking up power and needing to be cooled, you can argue maybe even zero OpEx. The other nice thing is this leverages open, standards-based, mature protocols that also requires minimal coordination with the content provider. If you think about how CDNs work today, they cache that data. They store that data. They need to secure that data. They need to participate in key exchange. There's a lot of coordination that needs to happen between the content provider and the CDN provider. You don't need any of that in this architecture because you're just forwarding packets. You're not storing anything. So you'll eliminate a lot of the complexity. By eliminating complexity, you reduce a lot of that cost. In terms of applicability, it's really any multi-destination content. You know, I've focused on sports, live streaming sports, because you know the top 3 use cases are probably sports, and then sports. You know, again, a quarter of all internet traffic on one night of the week is one football game. But there are other things that people like watching live. We live in an on-demand world. People are always going to watch Netflix movies, and that will probably always be, on average, the bulk of internet traffic. But there are certain things humans like live. Concerts, think e-learning, think worship services, think conferences like this. Isn't this a lot better being here? Interacting, seeing what it's like, than watching. You could be watching a YouTube video. Why are we all here, right? We could all be doing this over YouTube. Because some things are better live, right? The other use case that not as sexy, but arguably, tactically more useful is those, think distributing those large file OS updates, right? Imagine those days when you have to distribute, a multi-gig file to tens, maybe hundreds of millions of users all in the same day, right? Those things kill networks. So these big, multi-destination events, on average, they don't happen that often, but when they do, they create these spikes, and you have to plan for the spikes. It doesn't matter that on average that this doesn't happen. They're happening frequently enough that you have to plan for the peaks. The peaks are still the peaks. And that's what you have to plan and design your network to support. All right, so who's doing this? Is this real? There's actually, 3 notable and interesting TreeDN deployments, and I'll go through all 3 of them. The first one is a network called the deployment called UMetCast. So there's an organization in Europe called UMetSat. They're essentially like the NOAA of Europe, National Oceanographic and Atmospheric Administration. They're like that, but for Europe. And they operate a bunch of weather satellites that need to stream telemetry data on atmospheric and weather conditions. And these are high bandwidth, think 150 meg plus real-time streams that they need to get out to a bunch of research institutions and universities and the Weather Channel. So in the past, they'd done this via satellite, but that's really expensive. So they've a much cheaper option. They've been wanting to do this terrestrially. And so they have been using Multicast and sending this through Géant. And Géant, by the way, is the research and, I don't know if I mentioned this, it's the research and education network of Europe. It's kind of like the Internet 2 of Europe. And they have different member institutions. And so EUMETSAT would tell companies who wanted this content, organizations who wanted this content, connect via multicast to one of these members and you'll get the content. But a lot of them don't have, they're not on networks that are multicast enabled. So Géant has deployed a bunch of AMT relays. EUMETSAT sends the traffic. It goes natively to native receivers, and it leverages AMT to reach those end customers that want this data that are on unicast-only networks. It's been really successful. They've been very excited about it. They gave a talk at IETF. I encourage you guys. They're doing encryption and they're doing reliability. Really interesting stuff. Multi-factor authentication. Check out the talk. There's links to all of this stuff. Really interesting talk. By the way, I should mention the Géant chief architect was asked, why don't you just use CDNs? Wouldn't it be cheaper and easier than going through all this multicast stuff? And he said if he used unicast, traditional CDNs, it would be an order of magnitude more expensive than the multicast-based solution he's doing today. An order of magnitude more expensive. All right, a second deployment that's really interesting, and you can actually see this yourselves today, is there's several institutions, Internet 2 members, that are connected together. They have 4 public AMT relays, and they're delivering multicast streams that are on research and education networks that are connected to Internet 2 and to Géant. And they can send those streams anywhere on the internet. You can actually see this. There's a thing called the multicast menu, and you can see this in action. And this multicast menu essentially has a list of all the multicast streams, and you can click on them and launch VLC and watch this content. By the way, this portal, this multicast menu, was built by someone at the time. She was a 10th grader who was looking for an interesting project to work on during the pandemic. An extraordinarily gifted developer named Lauren Delwich. She's in college now at Yale and still working on this project, but this became her senior project at Thomas Jefferson High School in Alexandria, Virginia. And what she did was she took a script, really kind of clever, took a script that would reach out to the looking glasses at Internet 2 and Géant and go through every router periodically looking for multicast streams. Just show multicast route detail to find any stream that was had a packet per second rate of greater than 100, with the crude assumption that if it's greater than 100, it's probably video. And then populate a web page with the source and group information along with the nearest relay. You can also manually add your own streams, and you can add names to them. And she even added the ability to watch this stuff in a browser, which people thought was kind of impossible. She also added the capabilities to do off-net sourcing. So which is kind of an interesting idea. So I'm not going to go into it in much detail, but I'll just say, imagine you could send a unicast source stream, and there's a translator that's sitting at George Washington University, and that translator takes a unicast stream, does essentially NAT, turns it into multicast, and then it can go over this TreeDN network and be received by native receivers or off-net via AMT. All of this, Lauren gave a couple really exciting talks at IETF. I encourage you to check it out. By the way, we would love more content, more relays. For anybody else, for anybody who's interested in getting involved in this project, it's a fun project. If you can bring some content or a relay, I'll give you one of these shirts. Come see me. Be happy to talk about it if you want to get involved. I can be found at the hotel bar till close tonight. A third interesting deployment is the RareNet. And this is a research network run by Renatur, which is the research and education network of France. They basically took a bunch of P4 Tofino switches, some white boxes, and they implemented beer in P4. They implemented, the routing stack it uses is FreeRouter. They implemented ANT in that. And essentially they built a global network that distributes multicast via beer natively and via AMT. I kind of glossed over this, but we are not picky. And I've only talked about PIM SSM as the native part, but really we're not picky. You can use any protocol, any technology that, any forwarding technology. It could be PIM SSM, it could be MLDP, it could be beer, it could be TreeSID, you name it, point to multipoint RSVP. We don't care as long as it does SSM only, complies with the SSM service model. We don't care how you get those packets. And so this combination of beer and AMT is really exciting, really interesting. Jeffrey yesterday, my friend Jeffrey spoke about beer, an exciting, interesting technology. He was involved in this deployment as well. It's kind of, an interesting development. So, all right, so benefits. It's a more efficient utilization of network resources. So we can deliver existing content at an order of magnitude cheaper. So it makes existing stuff cheaper, and it also paves the way and enables new stuff that isn't viable for the network today. Again, a quarter of the internet traffic is one game, and it's not even in 4K. Think about AR, right? This is an architecture that paves the way for that. I talked about, if sustainability and reducing power and cooling and carbon emissions, from that perspective, from a sustainability perspective, we're eliminating racks and racks of x86. So this is a much greener solution. The other thing is, I work with a lot of large telcos, and they frequently lament that they've poured billions of dollars into their networks, and they're just treated like plumbing and a fungible commodity. And in the meantime, all those content providers are taking advantage of these poor phone companies and leveraging all their hard-earned infrastructure and reaching their eyeballs. And those content providers are the ones that are making the real profits. And these telcos, for all their investments, they want to wet their beak a little bit in some of that sweet nectar. How can we do that? Here's the answer. This is a technology, not only that can be useful for existing CDN providers, and they could leverage this for live streaming, but it lowers the bar and opens the door for service providers and other operators who have global reach to start offering replication-as-a-service, essentially CDN services. And they can do this at potentially zero cost if they have existing infrastructure that supports AMT. So, it uses an open standards-based architecture using widely deployed protocols, and it's much, much simpler and cheaper because, again, it eliminates a lot of the complexity and coordination between the content provider. We're not storing data, we're not protecting data, we're not securing data, we're not doing key management, we're just forwarding packets. So it's much, much cheaper, much, much easier. So here's the way to derive new revenue streams from your infrastructure and from your investments for all those large service providers. It also addresses some of the fundamental issues that we've had with network replication over the internet, talked about incremental deployment, leveraging overlay networking, something I didn't talk about, but multicast over Wi-Fi is kind of a headache. This solves that problem. The other thing is it healthy for the internet and society that nearly all distribution of content is handled by a handful of companies? Is that healthy for society? This TreeDN is a technology that gets us back to the decentralized roots of the internet, where any one person could put some content up and reach an arbitrarily large audience and enjoy the benefits of efficient delivery, where the marginal cost of each additional viewer is essentially zero, at least from the perspective of the source. So frequently asked questions. I'll save some folks some time who may be wondering a few things. What about targeted ads? What about key distribution? What about QoE and user experience telemetry? After all, SSM is inherently a unidirectional thing. How do you find out what's going on in the client? How does the client communicate back? The answer's simple. Just use unicast back channels. There's some things you need to get back from those receivers. Are they there? What's their experience like? You need to distribute decryption keys. You want to send them, bespoke ads. Use unicast for that. Set up a separate unicast tunnel, a unicast back channel. But for the stuff that everybody needs to get, use multicast for that. What about adaptive bitrate? That's a critical feature. There's different ways to do this. A simple answer is, the TLDR answer is just you put different groups, use different groups for different bit rates, and let the receiver pick the most appropriate bit rate for their that they're most capable of handling. The DVB MABR spec talks about this in great detail. I'd point you to that. Also, there's an interesting technology out called MAUD, Multicast Assisted Unicast Delivery, and they, similar to DVB, MABR, they talk about how to handle this. What about packet loss and reliability? Short answer: just use a forwarding. FEC, forward error correction. This is also covered in great length and detail in the DVB MABR spec. How about access control, right? How do we control who gets this stuff? You don't know who joined this traffic and gets it. Short answer is encryption, right? This is a problem with any multi-access interface. When you send stuff out and you don't know who's really going to get those ones and zeros, think Wi-Fi. How do you handle that? You just encrypt it. I'd point you to a spec called the multicast extensions for Quick. Jake Holland from Akamai was kind of the leader of that effort. A couple other folks working on that. That's a really exciting and interesting proposal that could solve a lot of these problems. All right, so up until now, we haven't needed multicast. Live audience sizes haven't been big enough for the last 20 to 30 years where multicast was never needed. Bit rates weren't big enough. But we're approaching an inflection point, maybe a crossing of supply and demand curves, where on the demand side, we're suddenly seeing on a regular basis tens of millions of concurrent viewers combined with larger bit rates coming down the pike to where maybe we need something different. Again, we haven't needed multicast because we haven't been in the situation that we're now in now. Audience sizes were just never big enough. But now, again, 59 million simultaneous viewers. That's a lot. So that's the demand side. And on the supply side, all the problems and complaints that people had 20 and 15 years ago, those are all irrelevant. Network-based replication has never been easier and more easier. Multicast has never been easier to deploy and operate. So that's essentially what TreeDN is. It's a model optimized to support this. So 20 years ago, with audience sizes and bit rates where they were and the complexity of multicast, a multicast-based solution, the juice wasn't worth the squeeze. 10 years ago, the juice wasn't worth the squeeze. Maybe 2 years ago, the juice wasn't worth the squeeze. But today, the juice is starting to taste quite sweet. And the squeeze doesn't require a whole lot of grip strength. So with that, I'll be happy to take any questions anybody might have until they kick me off.
Just a second. We do have a remote question from Matt Petach, unaffiliated. Good talk, Lenny, but this Tree CDN is only useful for real-time / live streams. Is there market evidence, demand evidence that there's any money to be made enabling SSM / AMT on resource-limited high-end routers just for the occasional football game?
Just the occasional football game happens once a week. It's a quarter of the internet traffic, and remember, it doesn't matter that it's just occasional, because that's what you have to design and plan your network for. It's 17% of all internet traffic right now, and it was less than 1% 8 years ago. EUMETSAT has said it's an order of magnitude cheaper to use this distribution mechanism than using traditional CDNs. So if you think everything is fine, we haven't needed it, so we're never gonna need it. If you're willing to, continue down the path of brute force unicast and you think we can do this forever and we can somehow solve the problem of live streaming AR, that thing I was talking about at the Golden State Warriors game, or that Kelsey suite with Taylor Swift, if you think we can do that, tens of millions of viewers can watch a live streamed AR stream on the internet today. Well, we can keep doing what we're doing. I just don't think, I think at some point the laws of large numbers assert themselves, and you can only ignore the laws of gravity for so long. So it radically reduces a significant headache for networks today, the cost of that, and it enables something that I don't think is possible today. Any other questions? Okay.
All right. Thank you, Lenny.